Welcome to the deep dive. We pull apart complex sources, extract the core knowledge you need, and do it quickly so you can stay informed. Today, we're really going deep. We're looking into the absolute foundations of the natural world. Our source is a comprehensive translated text, Introduction to Physics, or Fizik, bilmine, Giriş. Our mission. Well, first, to get a handle on the true scope of modern physics, but maybe more importantly, we want to grasp the learning philosophy this text really pushes the how of understanding it all. And along the way, we've got some genuinely surprising historical moments lined up, real aha insights into how the earliest scientists measured the cosmos without any modern tech.
Yeah, it's fascinating. The text kicks off by making it really clear that physics isn't some, niche academic thing. It's literally the language of existence. It shapes your daily life constantly. Think about the chip in your computer or medical scanners, MRI machines, even just how your car works. And then it scales right up to the structure of the entire universe. But the really critical part, I think, especially if you actually want to learn this stuff effectively, is the philosophy laid out right in the preface. It takes aim at the old way of teaching. It argues really strongly for focusing on conceptual understanding, deep understanding, not just, memorizing formulas like you might have done in high school.
Okay, let's dig into that because it sounds like a pretty big deal in terms of how you'd approach learning. But hang on, isn't physics full of formulas you just have to know? How does the source square this focus on concepts with, well, the sheer amount of math and facts involved?
Well, the argument is that just memorizing formulas doesn't really achieve much long term. That kind of knowledge, it tends to stay stuck in the classroom, right? The real value, the text says, comes from grasping the conceptual framework, understanding the actual reasoning behind why things happen physically. And that framework is what lets you look at any problem, even a new one, and start analyzing it conceptually before you even think about plugging numbers into an equation.
Ah, I see. So the math is a tool, maybe the language used to describe reality, but it's not the reality itself. So if you get the concept, you can apply the principle even without the calculation ready to hand. The why is the durable knowledge.
Exactly. That's the core idea. It
Yeah.
frames physics as understanding, well, everything. How nature works, living things, non-living things, buildings, stars, all of it. The goal is that the learning actually changes how you see the world. It encourages you, the learner, to constantly connect what you're learning back to real life.
That's a powerful approach. And it makes sense then that the source uses history not just as trivia, but to show this kind of thinking in action, right? It jumps back more than 2,000 years to these, well, incredible examples of early cosmic geometry. Where does it start us off?
It starts with Eratosthenes. He was the head librarian at the legendary Library of Alexandria around 250 BC. And the source credits him as being the first person to get a really accurate measurement of the Earth's circumference. And the way he did it's just brilliant in its simplicity.
Right, using just observation and basic geometry, he noticed that down in Syene, on the summer solstice, the sun was directly overhead at noon. Like sunlight went straight down a deep well, no shadow. But in Alexandria, further north,
At the exact same time?
there was a shadow, which proved the Earth's surface had to be curved.
Exactly. And he measured the angle of that shadow. It came out to about 7.2 degrees.
Okay.
Now, geometrically, 7.2 degrees is precisely 150th of a full circle, 360 degrees.
Ah, okay, I see where this is going.
So all he needed then was the distance between the two cities. Travelers apparently measured it out as 5,000 stadia. That's roughly 800 kilometers in modern units.
So he just multiplied that distance by 50.
Yep. Multiply 800 kilometers by 50 and you get 40,000 kilometers, which is incredibly close to the actual circumference of the Earth.
That is genuinely stunning. To calculate the size of the entire planet with sticks, shadows, and basic reasoning, no satellites, nothing.
Pure critical thinking applied on a massive scale. And then there was Aristarchus. A bit earlier, actually, he took that same kind of observational geometry even further. He aimed higher towards the moon and the sun.
Okay, how did he tackle that? The distances must have seemed unimaginable.
He started with lunar eclipses. By observing how the Earth's shadow moved across the moon, he estimated the moon's diameter was about 13.5 times the Earth's diameter.
So using the Earth itself as a kind of measuring stick for the moon? Clever.
Very. But his really bold move involved the geometry of a half moon.
A half moon, how does that help?
Well, think about it. When the moon is exactly half lit from our perspective, the sun's light must be hitting it side on relative to us. That means the Earth, the moon, and the sun form a perfect right-angled triangle with the right angle at the moon.
Got it. Like looking at the corner of a square?
Precisely. So Aristarchus measured the angle at the Earth corner of that triangle, the angle between the moon and the sun in the sky. Based on his measurement, he estimated the sun was about 19 times further away from Earth than the moon was.
19 times. Wow. Now, I know the actual number is much bigger, isn't it?
Oh yeah, much bigger. The sun is actually about 400 times further away than the moon.
So his measurement was off by quite a bit.
It was. But the text really emphasizes this. The methodology was the breakthrough. Using geometry and observation to even start putting numbers on the scale of the cosmos. That was utterly revolutionary. His imperfect results set the stage, for centuries of astronomy that followed. It showed it could be done.
That's a great point. The method over the initial result. Okay, so from the history of the method, the source then moves into the structure of the method itself, right? The scientific toolkit.
Exactly. Section 1.2 lays out the scientific method, which is obviously fundamental. This is really important for you as a learner to get this structure clear.
And I noticed it draws some really sharp distinctions between terms people often mix up, like theory versus law. What's the key difference according to the text?
Yeah, that's a common confusion. It defines a hypothesis clearly. It's a testable, educated guess, an initial idea you can check. A theory like the theory of evolution or atomic theory is much bigger. It's a well-established, comprehensive framework that explains a whole range of observations and facts. It's been tested extensively.
Okay, so a theory is an explanation. What about a law?
A law is different. It's typically a description of an observed pattern or relationship, often expressed mathematically, like Newton's laws of motion or gravity.
So a law describes what happens while a theory tries to explain why it happens.
You got it. That's the crucial distinction.
And the source also stresses that none of these are set in stone forever, right? Science corrects itself.
Absolutely. It makes a point of saying that science is always open to modification based on new evidence. It even brings up the huge shift from Aristotle's physics, which held sway for, centuries,
A very long time.
to Galileo's viewpoint. That's presented as a classic example of how established ideas must yield when the empirical evidence points a different way. Science has this built-in self-correction.
Which ties into the next section where the text sort of places science within the bigger picture of human knowledge.
Right. Section 1.3 briefly touches on science, art, and religion. It positions them as different ways humans search for truth and meaning.
How does it frame the differences?
It says science focuses on objective knowledge of the natural world, things you can observe, measure, test. Empiricism is key. Whereas art and religion often engage more with morality, ethics, personal meaning, belief systems, different kinds of questions.
And the implication is that they all contribute something valuable when they operate within their own domains.
Yeah, the text suggests that understanding is richest when these different approaches respect their boundaries and methodologies.
Okay, now that objective knowledge from science, particularly physics, leads directly to technology.
Technology is defined pretty straightforwardly as the application of physics. Computers, medical tech, energy production, communications, it all comes from applying physical principles.
But then the source adds something I wasn't expecting in an intro physics text, a section on risk assessment. That feels quite modern, quite ethically charged. Why is that in there?
It's a really important inclusion, I think. It directly confronts the fact that powerful technology inevitably creates risks. The text doesn't shy away from it.
No.
It mentions specific examples like handling toxic byproducts, managing nuclear waste safely, and the big one, resource depletion.
So it's building in a sense of responsibility right from the start.
Exactly. It basically says, look, we humans developed this amazing tech based on physics, but we are also responsible for managing the downsides, for thinking about safety, environmental impact, and, crucially, the consequences for future generations.
It's an ethical mandate woven into the physics curriculum itself.
Pretty much. It moves physics beyond just equations on a page.
That's quite profound for an introduction. Okay, so to wrap our heads around the sheer scope of what physics covers according to this text, the table of contents itself is revealing. It's like a roadmap. What are the big chunks?
It's structured into 8 main parts, giving you a path from classical foundations right up to modern concepts. Part 1 is mechanics. Newton's laws, energy, momentum, rotation, the basics of motion and forces.
The absolute bedrock.
Then Part 2 is properties of matter. This gets into atomic structure, how solids, liquids, and gases behave. Part 3 covers heat temperature, heat transfer, and the big laws of thermodynamics.
Right, mechanics, matter, heat. What's next?
Part 4 is sound, vibrations, waves, how musical instruments work. Part 5 is a huge one. Electricity and magnetism. Covers everything from static electricity to circuits, motors, generators, electromagnetic induction.
Foundational for basically all modern technology.
Totally. Then part 6 is light. Reflection, refraction, lenses, but also wave properties, interference, and the concept of photons.
Getting into the quantum nature of light there.
Exactly. Which leads into part 7, atomic and nuclear physics. This is where quantum theory really takes center stage. Radioactivity, nuclear structure, fission, fusion, it's all in there.
And the final part.
Part 8 is relativity. Both Einstein's special and general relativity theories are covered.
Wow, that's
Yes.
comprehensive doesn't quite cover it. It runs the gamut from basic motion to the fabric of space-time.
It really does. And it shows how the field keeps growing. The source makes connections to modern applications and discoveries, too. It mentions things like fractal antennas, showing how geometry impacts modern tech, and even the search for the Higgs boson, linking back to fundamental particle physics. It bridges the ancient and the cutting edge.
So this deep dive really paints physics not just as a list of facts to memorize, but as a structured way of thinking. A self-correcting method for understanding, well, pretty much everything.
I think that's the biggest takeaway. What stands out, going right back to Eratosthenes and Aristarchus, is that the foundation was about questioning assumptions. It was about using rigorous, testable logic. That approach, the method itself, and the philosophy of learning it conceptually, not just by rote, that's the core lesson this source seems to want to impart.
It leaves us with a lot to think about. And here's a final thought for you, connecting back to that section on technology and risk. Given the incredible power that comes from applying physics, think nuclear energy, AI, which relies on computation, genetic engineering informed by biophysics, the source clearly implies we need constant vigilance. So how should the global scientific community, and maybe society as a whole, prioritize assessing those big, long-term global risks when technological progress often moves so much faster than our ability to fully understand or regulate its impact? Something to consider as you notice the physics playing out in the world all around you.